In this video, we're going to go over tests of difference and show examples of t-tests and one-way ANOVA. So tests of difference are tests that conveniently test for differences between groups in this case. So one of the common examples that you'll see is when you're doing a drug trial and you want to compare two treatments or drugs to a control group that might be a placebo. So that's what this graph on the right shows. You see the first blue bar shows the control group, the red bar shows one drug, and the green bar shows a different drug. And here we see the green bar is pretty different from the control and drug A, but the control and drug A are pretty similar to one another. The example data that we're going to be using to illustrate how to do this in SPSS comes from a study that we did here at Fordham that tested people's trust in statistical algorithms to make predictions about different types of events. Trust was measured from 0 to 100, and an example of a statistical algorithm making a prediction would be something like 538.com's election forecast model. So here you see on the right what this forecast looks like, and this is a statistical model that's predicting the outcome of the upcoming election. And you might want to take a second to think about what you think about this model or what you think about models doing predictions on elections means to you. So first, we're going to think about independent sample t-tests. And these look at the difference between two different groups on a continuous dependent variable. So in our data, we asked different people about their trust in statistical algorithms for questions that were about political predictions, and also other people about questions that were about economic predictions. And we want to see if there's a difference. Do people have more trust when the predictions are political, or do they have more trust when the predictions are about economics? So to test this, we can hop on over to the SPSS window. So to do a t-test, we select Analyze. We go to Compare Means, and we select Independent Samples t-test. So our dependent variable goes up here in test variables. In this case, this is RESP. This is the 0 to 100 scale of trust in statistical algorithms. And then we want to put item domain in the grouping variable. So this is whether the domain was economics or politics. So now we can define the group. We can just put two different numbers in here. We need to say they're 0, 1 or 1, 2. This is somewhat arbitrary, but you need to do this to run the test. Click Continue, and then run the t-test. So up here at the top, you see you've got a group statistics table. So this is the descriptive statistics broken down by group. You see the sample size. There were 114 observations that were about economics. 114 people got asked about trust in algorithms for economics, and 136 got asked about trust in algorithms for politics. Then we see the mean rating, the standard deviation for the rating, and the standard error. And then here at the bottom, you see the results of our test. And I'll hop on over to an editor window so we can go over this. What we're interested in here is everything that's in this section. We don't care about these first two rows on the left. We care about these last rows on the right, the columns. We don't care about these first two columns on the left. We care about all these columns on the right. The first column is the t-test. The next is the degrees of freedom, the significance, the difference between the two means. And then all the way on the right, we have a confidence interval for this difference. And the two different rows just represent two slightly different tests. It's not a huge difference. In this case, it's just about whether the standard deviations are equal between the two groups or whether you can assume that they should be. You can just use the bottom one if you're not sure, but for the most part, it's not going to make a big difference. So let's go back over to our slides. So these slides just show the same thing again, and here's the output. And now we're going to talk about effect size. So effect size for independent sample t-test is called Cohen's d, and conceptually Cohen's d is fairly straightforward. It's the difference in means divided by the standard deviation. However, we have two different groups, and they have two different standard deviations. So we need to use what's called the pooled standard deviation, and this is a bit trickier to calculate by hand. Unfortunately, SPSS doesn't do this for us, so we have to calculate it on our own. However, fortunately, there is an online calculator that will have everything we need. So let's go back over to this window here. So everything we need is actually up here in the group statistics table. So what we need is the sample size of each group, the mean of each group, and the standard deviation of each group. And once we have those, we can go over to the web tool that we have, And you can see I've already entered them all in here. These are the mean of group 1, the standard deviation, and the sample size. Mean of group 2, standard deviation, and sample size. I click calculate, and it will do this for me. There it goes. Now I scroll down. Hopefully. There we go. So here we go. And now we have Cohen's d down here at the bottom is 1.68. There are a couple other types of effect size down here. Don't worry too much about those. We just need Cohen's d. Back to our slides. And this just shows that same thing we just looked at again. So now we'll talk about one-way ANOVA. So t-tests help us compare two groups at a time. But what if we have more than two groups? And that's where one-way ANOVA comes in. One-way ANOVA allows us to compare more than two groups at once. So a better conceptual example would be like what we looked at in the first slide, where we had a placebo and then two treatment drugs. There we have three groups. We have the placebo, the control, and then we have drug A and drug B. And we want to compare all three to each other at once. And we can't do that with a t-test, but we can do it with one-way ANOVA. In our example, what we're going to look at is whether trust in algorithms differs by employment status. This is one of the only variables in our data that has more than two groups. It's not necessarily a great example because do we really think that this is going to vary by employment status? Maybe students have a lot of trust in algorithms. Maybe people who are retired don't have much trust in algorithms. I don't know. I don't have a strong hypothesis about it, but it's still an example that we can look at in our data. So we're going to go over back to the SPSS window. We're going to once again start at the Analyze menu. We're going to go to Compare Means once again, and this time we're going to select One-Way ANOVA. I already have it. I'm just going to reset it. This is what it'll look like when you open it up. So you are going to put your dependent variable in the dependent list, in this case RESP, our dependent variable, and we're going to put our grouping variable in the factor list. In this case, this is employment status. And then we're going to click Post Hoc, and we're going to select Tukey, which I will explain shortly. And then we will click Options, and we want to click Descriptives just to make sure we get our descriptive statistics. And then we run, and this gives us our one-way ANOVA output. So at the top here, you see you have descriptive statistics for each group, and then at the bottom, you also have for the total group. So you have each group separated out, and then in total. And then we have this ANOVA table and this multiple comparisons table. And let's take a look at what these do in the editor. So the ANOVA table is our inferential test. This is where we're testing for the statistical significance of whether there's a difference in at least one of the groups from all of the other ones. So this is an F test. So you see over, try it again. Clear it out. There we go. So there's the F test and there's statistical significance. And remember that F tests have 2 degrees of freedom. So here we have degrees of freedom are these first two, 5 and 244. And then we also need to take a look at this multiple comparisons table. So what this multiple comparisons table is doing is it's doing individual t-tests between each pair of groups. So you see here we have, this is the first group employed full-time, and each row now is comparing employed full-time to each other group. So this first row here is a t-test between employed full-time and employed part-time. And here we see the mean difference and the statistical significance, in this case, not significant. And this is what we did when we set the Tukey option before. So think about it this way. If you make comparisons between one group and 5 different groups, and then another group and 4 more different groups, that's already 9 tests. And so we're doing a lot of different pairwise comparisons here. So the chances that one of them is going to wind up being a big difference just by chance alone is pretty high, and we want to account for that. And that's what the Tukey test does. It makes our tests a little bit more conservative so we don't run the risk of making what's called a type 1 error. And of course, since these are t-tests, we need the degrees of freedom, and the degrees of freedom are, we can go back to our descriptives table to get that. It doesn't report it for us automatically, but if we're comparing, for example, employed full-time to part-time, we actually want to take the sum of the two ends minus 2. So here we have 180 and 35, so that is 115 minus 2 is 113. That's your degrees of freedom for this t-test. And this is just going over all that once again. That's how you get your degrees of freedom. So now we'll talk about effect sizes. So there's two different effect sizes we can think about with one-way ANOVA. The first is the omnibus test, which is, again, looking at whether one group is different from all of the other groups, or whether the group differences explain variability in an independent variable. So we can, for this effect size is an effect size that is across all groups. This is just a general effect size for all groups. And this is called eta squared, which is this little funky Greek letter squared, eta squared. And the way we get this is we divide the sums of squares from between groups by the sums of squares total. So we can go back and look at where we get this from. It's from this ANOVA table up here. So we get sums of squares between, it's the top row, and sums of squares total is this bottom row. We divide the top row by the bottom row, and that gives us our eta squared, and it's going to be between 0 and 1, in this case 0.02. And then the multiple comparisons are t-tests, so we can just do Cohen's d just like before. So we could plug in the n from employed full-time, the mean and the standard deviation, as well as part-time, again, n, mean and standard deviation, into our calculator from before and get Cohen's d just like before. These are some benchmarks for effect size. So for Cohen's d, a small effect would be 0.2, medium 0.5, large 0.8. For eta squared, small would be 0.01, medium 0.04, and large 0.14. And here are just a few examples of other things you can do with tests of difference that we didn't cover here. Most of you will be okay with what we covered, but if you need to, we can go into detail individually on some of these other ones. So a paired sample t-test looks at differences in the same group after something changes. So this might be a repeated measure of something. So for example, let's say you take the SAT, you don't do so well, you take a Kaplan course, and you take the SAT again. If you study a bunch of people who all go through the same thing, that would involve a paired sample t-test, and you can extend this to more than 2 repeated measures with repeated measures. ANOVA. Two-way ANOVA is the testing for differences between multiple crossed groups. So, for example, you might say, is trust in statistical algorithms different by gender and by item domain? So these are crossed groups, so men and women might see politics and economics. They're not tied to one another, so this is 2 sets of groups that we're comparing at once. ANCOVA is testing for differences between groups controlling for another continuous variable. So let's say we wanted to control for age, then we could run an ANCOVA. And then MANOVA is a test of differences for more than one